So we're looking at, it says plot and interpret distance time graph. Well, first of all, a distance time graph um, is basically a graph with time along the x-axis and distance along the y-axis. It's changing, it's measuring, or it's showing how distance of an object is changing as time increases. So if something is moving, then as time goes on, the distance is going to increase, because when you move, your distance increases. So you would see the distance going up when something's moving, and when it's not moving, it's going to be flat. We'll look at some examples of this in a moment. But basically, a distance time graph is time along the bottom, distance along the side, and knowing how to plot them, and also knowing how to understand the shapes of them. We've got some questions about that over here by the looks of it. Like, there we go. So distance along the side, time along the bottom. And then we've got a speed time graph, and then underneath we've got an acceleration time graph. Let's go back to here then, and let's go back to the checklist. What else have we got? I'll just lock that. So calculate speed and average speed. So how do you calculate speed? So we'll look at what that means in a moment as well. I'm going to just briefly go over all of them, and then we'll go through each one in detail. Plot and interpret velocity time graph. Very similar to distance time graph, only it's velocity against time. Velocity is basically the same as speed, but not quite the same. And yeah, so plot and interpret that, very similar to distance time graph. Calculate acceleration. So we're going to look at how to calculate acceleration, and also going to look at how to calculate acceleration and distance from velocity time graph. Now, this is a bit more advanced, this one here. So this is looking at the gradient of a graph, and also looking at the area under a graph. So we'll look at that in a moment. Describe experiments. What kind of experiments are there to determine speeds and accelerations? So there's probably going to be some experiments which you might have learnt about, and you need to be able to describe them. This is a formula a lot of people get very scared by. It's not as scary as it looks. The V stands for velocity. The V stands for final velocity. The U stands for initial or starting velocity. And then you've got A for acceleration, and this is actually displacement, very similar to distance. So what it's saying is if you could rearrange this, and let me just show you how I would rearrange it so as it makes a little bit more sense. So I'll just get a green pen here, and what it's saying is that V. So let's just square root both sides. If V squared is equal to all of this, then V is equal to the square root. Let me just try drawing that square root sign again. It's equal to the square root of U squared plus 2AS. Okay, you don't really need these brackets actually, but we'll put them anyway. Describe the effects and forces on objects, and draw forces on the objects. So yeah, what happens when you push something, or what happens when something's rolling, like maybe an object is floating in space, what forces are acting on it. It's got gravity or weight acting on it, and if it's moving, it might have air resistance acting on it as well. So I mean, this is a very vague thing, and we'll have to look at some examples of this. Distinguish between vector and scalar quantities. Does this ring a bell at all? In a nutshell, vectors are something that has size and direction. Scalars are something that has only size, or another word for size is magnitude. Earlier on, when I said displacement, basically the same as distance, and I said velocity is basically the same as speed. Velocity and displacement are vectors. Speed and distance are scalars. So you could have, if I said I'm traveling at 5 meters per second, well, that would really mean I'm traveling 5 meters per second forwards. If I was traveling negative 5 meters per second, it would mean I'm traveling 5 meters per second backwards. So in that case, I'm describing a vector. There are some things that cannot have a vector. For example, temperature. Now, although temperature does have a negative value, it doesn't mean, if I say it's negative 5 degrees outside, I don't mean it's 5 degrees backwards. Doesn't make any sense, right? So that would be a scalar. Temperature would be a scalar. So there's a few things that are scalars, a few things that are vectors, and there are actually a few things that can have a scalar or vector version. For example, distance and displacement. They're very similar, only displacement's a vector and distance is a scalar. Resultant forces acting along a line. What this means is, like this example here, let's say the weight is equal to 3 newtons and the air resistance, we'll just call R, is equal to 1 newton, then the resultant force would be 2 newtons down. So it's like, what is the, it's like the total force, or what is the result of the two forces, the resultant forces. When you put them together, how do they work together? That's what resultant forces means. Identify and describe different types of a force. Well, you probably want to be talking about, is it a push or a pull? And is it a contact or a non-contact force? What that means is some forces, they don't need to be touching anything to apply the force. So gravity, if there's a ball floating in the air, it's going to feel the force of gravity. There's nothing touching it though, so that's a non-contact force. Same with magnets. Magnets is a non-contact force again. You get two magnets close to each other, they're going to attract or push away from each other. They're not touching one another though. Whereas something like friction, that's a contact force. So friction is caused by something touching, and there applies a force there. So that's probably what it means there. Nearly at the end now. F equals ma. F is for force, m is for mass, a is for acceleration. What that is saying is that it's better understood if I rearrange the formula. Acceleration is equal to force over mass. So what this means is, if I had an object, let's imagine I was pushing a block and I was to the right, and I applied a force of 3 newtons, and let's say the object is 2 kilograms, then what it's saying is the acceleration is going to be equal to the force over the mass, which in this case is equal to 3 over 2. So oops, didn't mean to do that. How do I get back? If you want to know how to navigate, opportunity to show you how to navigate yourself around the board, a couple of ways. You can get the map back up again, and you can find roughly where it was, probably around about here. No, that's chemistry. Okay, and then if that's a bit tricky, then you go to the magnifying glass, and we were doing motion, force and motion. So we click on force and motion, and we're back to the whiteboard we were looking at. So quite useful to know how to navigate yourself around this. Right, where were we? So that's really all that means. F equals ma. It's actually otherwise known as, I think, Newton's second law, but it can be more easily understood as A is equal to F over m. So the acceleration is clearly going to be bigger if the force is bigger, and it's going to be lower if the mass is bigger. Okay, right. Describe the forces acting on a falling body. I did that a moment ago, actually. If something's falling, you've got the weight acting on it, and then you've got the air resistance acting on it. But it does get more complicated than that. Describe the factors affecting stopping distance. Stopping distance, let's very, very briefly go through this. If you've got an object here that is going to cause a problem, then like this car is driving along right here. This is supposed to be a car. And it's driving along at, let's say, 10 meters per second or whatever. It doesn't really matter what the speed is right now in my demonstration. We want it to be able to not hit that object there. So eventually it puts on its brakes, but it doesn't put on its brakes straight away because he has to react to it. Let's say at this point here, he sees the object, but it travels a short distance before eventually reacting and putting on his brakes. And then he travels a little bit further before his brakes finally come to a stop. So the total distance between him seeing the object and coming to a stop is the stopping distance. And then the distance between him seeing it and reacting is called the thinking distance. And the distance between him putting the brake on and actually stopping is called the braking distance. Okay. And I think that's the whole checklist. So that's a brief summary of your checklist.